D4 reflection solution. So let's start with problem 1. For which of the following values of n and p is a normal approximation appropriate? So I'm first going to use staplets. So basically what I did is I went ahead and put these values in. By the way, the answer is D. But here, let's go. So I put the values in and I get for n is 100 and p is 0.95. You can see that there's definitely some skew to the left. For n is 100 and p is 0.07, there's some skew to the right. For n is 15 and p is 0.5, it looks symmetric. It's looking a little close, but it's a little chunky. For n is 30 and d is 0.6, then we get, you can see how it's hugging the more normal curve more. And by the way, let me go ahead and get my laser pointer. You can turn on the normal curve. You can see that line right there. So you can turn that on and staple it. And then finally, the last one, you can see that there's a little bit of skew. It's kind of like shifted a little. So how do we figure this out numerically? Well, there's a very simple rule. We check that n times p is greater than 10 and n times 1 minus p is greater than or equal to 10. So we need at least 10 theoretical successes and 10 theoretical failures. So my first choice, I calculate, and I have 95 successes and 5 theoretical failures, 7, and then less than 10, because it's so that's already less than 10. I don't have to check n times 1 minus p. So I have less than 10 theoretical successes, so I can already skip on. For C, I also have less than 10 theoretical successes. I only have 7.5, so move on. For D, I have 18 theoretical successes, and so I have to check failures, and that's 12. Both are greater than 10, so D looks appropriate. And then finally, for E, I have enough theoretical successes at 24, but I only have 6 theoretical failures. So the correct answer is D. For a binomial model with n equals 80 and p equals 0.7, what is the z-score for x equals 58? So what we have to do is remember our formulas. We're going to need mu and sigma. All right. Now, it doesn't matter if it's normally distributed or not, because this is the mean and this is the standard deviation for this binomial distribution. And we just go ahead and calculate that, and that's all you need for a z-score. Z-scores are not just for normal distributions. So there's our mean. There's our standard deviation. 80 times 0.7 times 0.3, take the square root. Plug in our values, and we get 0.488, which rounds to 0.49. Problem 3. For a binomial model with n equals 80, so n p equals 0.7, above what value would be considered unusually high using normal approximation? So let's go ahead. You're probably tempted to say, well, the highest one there, it could be. So highest 5% is unusual. And actually, let's see, 0.3. This one we can use a normal approximation because the number of theoretical successes is 56, which means the number of theoretical failures is 24. So the z-score for the highest 5%, I did inverse norm. You could use staplet to get the value. You need to start practice using the calculator. That would be good. It's 1.645. So I'm going to get my z-score. I have my mean already and my standard deviation, which I calculated in the last problem. And I solve. And I get x is 62.7. So it wasn't the highest value. 62.7 marks the cutoff for high values. Anything above that, yes, would be considered unusual. So 62.7. Number 4, what would be unusually low? So that would be the lowest 5%, or the 5th percentile. Inverse norm is 0.05, which gives me negative 1.645. So it makes sense because we are using a normal distribution or normal approximation. It should be symmetric. Here's my z value, or my formula, and then I substitute in, do the same math, and we get 49.3, which, whoa, why do I not have typo? So I will fix that in the problem. It is 49.3. instead of 47. One of those will change to 49.3. So, all right. So you probably won't even see the wrong answer there. I did. It's on your handout. I need to go fix it. For a geometric model with 0.8, what is the probability that the first success occurs on the fourth attempt? So this is straight from your math chart. Excuse me. And I know I'm looking at the fourth attempt, p equals 0.8. So I basically just substitute in x is 4 and p is 0.8. Calculate. By the way, if you do it with the calculator, it's PDF. P is a geometric probability distribution function. It does it for one discrete value. And in this case, it's doing 0.8 and it's doing x equals 4. And you get 0.0064. Number 6, for a geometric model with 0.8, what is the probability the first success occurs sometime after the fourth attempt? So we have probability that x is greater than 4. That's 0.8. And so we go ahead and we calculate, oh, we'd have to do this forever. So I'd have to do it for x is 5, x is 6, etc. Or I could do the complement, which would be 1 minus the probability x is less than or equal to 4. So 1 minus all of that, which in calculator terminology is cumulative distribution function. You see that C right there? That's important to note. So that will do everything from 0 to 4. And so 0.8 x equals 4. Plug that in, and we get an answer of 0.0016. Okay. For a geometric model with p equals 0.8, what is the average number of attempts to get to the first success? Super easy. First of all, we know p is 0.8. Mu of x is 1 over 0.8. Oops, my formula came after. So if x has a geometric distribution, if you look on your formula chart, there is a formula. You just do 1 over 0.8, and that gives you the average number of attempts to first success. So I just did 1 over 0.8. For a geometric model, what is the standard deviation? So here's the formula, and I substitute in, calculate, and I get 0.559. You can see 1 minus 0.8 over 0.8, so there's my answer. Number 9. What are the mean and standard deviation for the payoff variable? Now, you can use technology. You could put these both in a list. List 1 and list 2, and then do 1 var stats. Make sure you use both lists. This one is the frequency list. But this one's easy to do by hand, and I strongly recommend you know how to do these by hand. We will expect this. If this is like the only question on a free response, you should show us by hand because it's not that hard. So we have e of x, and then I have each outcome times its probability, and then I add them up, and I get 375. Sigma is a little bit harder, but it's not that bad. So I actually do the whole thing here. Each outcome minus the average or expected value, 375. Square it. Some of you did not square everything. Then multiply it by its associated probability. And then when you're done, take the square root, which gives you 1083. Number 10. Suppose 80% of jurors come to a just decision. In a jury of 6 people, what is the probability more than half come to a just decision? Well, more than half means that x is greater than 3, right? We know n is 6, p is 0.8, and x is greater than 3. So we're looking at the count of successes for a fixed number of trials. This is binomial, not geometric. We can't use a normal distribution because n and NP and n times 1 minus p can't be greater than 10. Our total is 6. And our outcomes we're looking at are 4, 5, and 6. So we have to calculate those probabilities. Or it's faster if you're doing calculator to do the left probability. And so we'll do x is less than or equal to 3 and do a 1 minus. So binom CDF, our trials is 6. Our probability is 0.8, x equals 3. And we subtract, and we get 0.90112. Number 11, a real estate agent working entirely on commission weekly makes an average of 850 with a standard deviation of 260, selling property in the city and an average of 1340 with a standard deviation of 390, selling property in the suburbs. And assuming independence of what she sells in the two locations, what are the mean and standard deviation of our total weekly sales? So these are two different measurements. This is combining random variables, not transforming, combining. The mean is easy. We just add those two, right? So there you go, 2190. So we know it's C, D, or E. So we're just adding the 850 and the 1340. All right. Standard deviation, on the other hand, we have to work in variance because we are combining two measurements. We're doing her city sales and her suburb sales. I presume it's a her. I don't know. Yeah, it said she. So the variance of the total is the variance for the city plus the variance for the suburbs. So I have to square those sigmas. So the sigma for city was 260. The sigma for suburbs is 390. Square them, add them up. Then take the square root, and so your standard deviation is 469. 12 through 14, STEM plots. So here's a STEM plot for the percent of residents aged 25 to 34 in each of the 50 states. And they ask, why did they split the stems? Well, you can see that I would only have, I would have 6 stems. It would be kind of hard with only 6 stems to see shape. So if we had not split the stems, most of the data would appear on just a few, making it hard to identify shape. An appropriate key, well, it was tempting to say the 9, but that one isn't actually in the stem plot range, but 16 is an actual value. So we always take the left side of the stem, the right side of the stem, with a line between, and then say that's O, and then translate it to a value, so that's 16.0%. And of that state's residents are age 25 to 34. They said it was a stem plot of, here, let me go back to it. It was a stem plot of the percent of residents age 25 to 34. So that's why we knew it was percent. All right. Next one. What is the shape? It's tempting to say that this is skewed right, but if it is, it's super minor. I would say this is roughly symmetric. You really need strong skew before you start saying things are skewed, all right? And especially since it says clearly here, it's not clearly left or right skewed. It is roughly symmetric. So let's start saying when it's kind of hard to tell, let's say roughly symmetric. When it's clear, go ahead and say what it clearly is. Last but not, or last or second to last? Second to last. You read in a book about bridge that the probability that each of the 4 players is dealt exactly 1 ace is approximately 0.11. This means that, first of all, anything that says exactly, ignore. Exactly, bad. Very close, this one looks good. C looks good. But this says the average number of aces, and that's not what we set up there. Okay, this is a good start. Very large number of bridge deals. Has 1 ace. Aha, this looks more, right? So it is D. Gets an ace in only 2 of the first 50? I don't know. All right, so there you go. Last but not least, number 16. The most common bet in craps is the pass line. A pass line better wins immediately if either a 7 or 11 comes up on the first roll. This is called a natural. What is the probability a natural does not occur? So I'm going to find the probability of a natural first, which is 7 and 11. And I get 8 over 36. All right, tempting to say that's the answer, but it says does not occur. So I have to subtract that from 1, and I get 28 out of 36. And that's it.